Okay, yeah, thank you very much for the very nice introduction and for the invitation. It's a great pleasure and honor for me to give a talk at this event. I would also like to congratulate the organizers. I think it's a great idea to organize in these times, in particular, a virtual conference for, in particular, PhD students. Now, I would like to speak about mathematics of deep learning, and I think everybody knows about deep learning. It's more and more around us. It's the workhorse also of artificial intelligence. Still, from a mathematics viewpoint, it's more or less still like a black box. And so what I would like to talk about in this talk is, can we open this in some way? Because there's a lot of exciting mathematics going on these days. Now, as I said, deep learning is all around us. Everybody knows about self-driving cars, surveillance tasks, also legal issues. So for instance, for job applications, they are sometimes now already pre-screened by neural networks, and also the whole healthcare sector. So for instance, in the imaging modalities, their neural networks are often now used, and also for reaching decisions. Still, from a mathematics viewpoint, one has to say that there are very few theoretical results really explaining their success. There are more and more these days. It's an exciting time. A lot of people from various different areas of mathematics, theoretical computer science, statistics, and so on jump the area and bring in their unique tools. Now, so there are very few theoretical results, and I think this is also recognized in various other communities. There was an interesting incident, basically 2 years ago, at an AI conference in San Francisco. There was a researcher, Ali Rahimi, who works in artificial intelligence at Google, and he gave a plenary speech. And during this plenary speech, he said, machine learning algorithms in which computers learn through trial and error have become a form of alchemy. Researchers, he said, do not know why some algorithms work and others don't know, though they have rigorous criteria for choosing one AI architecture over another. And so there was a heated discussion in that community whether this is true and to which extent now, theory needs to be developed. From my viewpoint, I like very much what actually Stephen Hawking said. He said, the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. And I think in particular in this area, sometimes we think that we already know enough, but in fact, for instance, for sensitive applications, there's a great need to really delve deeply in and understand from its depths why these methods work. And in fact, deep learning and deep neural networks are very theoretical and very mathematical. So what is a neural network? Please first take a look here. So it's basically a function from RD to some RNL, where NL is typically chosen to be equal to 1, for instance, if you do classification. And as you see, it's a highly structured function. So these capital T's are affine linear maps. So AX plus B, we'll see that in a bit more detail on the next slide. Now, we don't want to do anything just linear. We need to bring in some nonlinearity. That is done by this function rho. You see it's a univariate function. It's called activation function. And because it's univariate here, it's applied component-wise. And then we apply next affine linear map and so on. And important characteristics, as for instance, what's called the number of layers here, so which is the number of affine linear maps. Now, typically, if you see something about neural networks, you see pictures like this, so graphs. So how is this related to this formula here? Now here we have as input dimension 4 are 4, so we have here x1, x2, x3, x4. Then these connections mimic this affine linear map. We'll see that in more detail on the next slide. Then I apply the activation function in these components. So here I have a map from R4 to R5. And then I keep going with the next affine linear map and so on. So this is the connection. And you see now how, let's say, so here, sorry, here the end neuron is just 1. So here we map from R4 to R1. So what is the detailed relation between these affine linear maps and these connections? So let's make an example. Let's assume I have this matrix for my affine linear map. So this maps from R3 to R3. So I have 3 neurons here. And the component of my output is this times x1 plus this times x2. This is mimicked by these two connections. The second output is this times x3, which is this connection. And the third component of the output is this times x3, which is this connection. Then I have here this what's called bias. And here the entries of the bias I apply in these neurons. Then I apply here also the nonlinear functions, the activation functions, and then I keep going. So the next affine linear map would map from R3 to R2. And this is mimicked by these connections and so on. Yeah, but you also see now if you want to have very few connections, which is called sparsely connected, then what you need is a lot of zeros in these matrices. Okay, so what do you do with a neural network? Well, I mean, you have a complicated function in the background. So for instance, a function which is defined on some manifold, some lower dimensional manifold, maybe something like this. And let's assume people in computer science like to separate cats from dogs. So let's assume in one area we have images of cats, in the other area we have images of dogs. And so the function now in this area maps all those to, let's say, the value 1 and all those to the value 2, so for classification. But what we have at hand are only sample values. So we have for a couple of pictures, we have the correct value, either 1 or 2. And from these, we want to learn the function f. How do we go about if we want to do that with a neural network? Well, I mean, first we actually have to select the architecture of the neural network. And so there are a lot of free parameters. We need to choose how many layers to take, how many neurons in each layer, which activation function. Maybe we don't want to take what's called a fully connected neural network, but we want to just select some collections, so that requires us to put zeros in these matrices. Okay, so let's assume I have collected, I have chosen an architecture, then I need to train my network. And what I do is I learn these affine linear functions, so the entries of these matrices and the entries of the bytes. And the way I do it is by an optimization procedure. So what I want is that the resulting network evaluated in these sample points is close to my function values in these sample points, which are known. And the closeness I determine by a so-called loss function. So that would be, for instance, the square loss, so the difference squared. Then maybe I would like to incorporate additional properties of these matrices and these biases, maybe that they are sparse. So this is done by this regularization term. So maybe I put the L1 norm on those. And then I minimize. So I choose these weights and biases, which give me the minimum. This is usually done by what's called stochastic gradient descent. And then finally, I get a network out, and I hope that this network is actually close to my initial function. And you see, actually, from this, now all the theoretical questions arise. And they can be separated in those areas. So first, expressivity. Which architecture do I choose? How powerful are network architectures? Can they represent the correct functions? That requires a lot of approximation theory, applied harmonic analysis, and so on. Then the second, the learning part. I have a learning algorithm. What are good starting values? Does it converge? At which rate does it converge? Because that's a non-convex optimization problem, which is very hard to handle. And so this requires differential geometry, optimal control, optimization. And then generalization. So that means I only know sample values, but I want certainly that in the end, my neural network also performs well on other data, which it hasn't seen before. And that's called generalization. So that requires learning theory and so on. So these three components are, if you're familiar with statistics, exactly the components of the statistical learning error, which is the approximation error. You have an approximation class, and does what you want to approximate belong to it? How close is it? Then the error you have from the algorithm itself, and then you have the error because you just have sample values. And there's another area which I think is also very exciting, which is called interpretability. So I have a trained neural network. I don't know how it's trained. It's just there. And I want to understand how it operates. And that will be a situation which one encounters numerous times in the future. And that requires tools like information theory, uncertainty quantification. Now, in this talk, I would like to focus a bit more on the area of expressivity, which is maybe the most explored of those areas which you see here. And then I would also delve a bit more into the area of interpretability, which is maybe the newest of those. But before I do that, I would like to also tell you why and how I actually became interested in this whole area. And that has to do with the impact of deep learning on mathematics, on mathematical methods. So my background is mainly from the area of inverse problems and imaging sciences. And I think tomorrow you will hear, I'm sure, an exciting talk by Carola Schönlieb in that direction. Now, in that area, one could see that neural networks were extremely effective. Why? Well, I mean, an image, there's no really a physical model for what an image is. And so therefore, it's very accessible by data-driven methods. The area of partial differential equations was a bit slower to embrace this new method because it's not really clear initially why we need it. Because we have a physical model, it's there. There's nothing to be learned per se. But I mean, it turns out that in a high dimensional regime, these methods are very effective and can beat what's called the curse of dimensionality. And so I'd like to just very briefly show you, I mean, to maybe arise also your interest in those, let's say, directions, just very briefly what we did in these areas, just with a couple of slides, and then we will delve into, as I said, expressivity and interpretability. But there are actually many more papers than what I have on this slide. Okay, so the first is limited angle computed tomography. So I guess you're all young, you have never experienced lying in a CT machine, but still, what does this CT scanner do? If this is the human body, it computes line integrals through it, and this gives me one slice of the sinogram, and then I rotate. So this is the so-called radon transform. It becomes really hard if I cannot rotate the full 180 degrees. I'm missing a chunk, so basically I just have a part of this what's called sinogram, and from this I would like to recover. But since I'm missing a huge chunk, that's an extremely difficult problem. And so what we did, and I think this is a very general conceptual approach to such problems, is we used the methods which were done before without deep learning as far as they are possible. So we used what's called sparse regularization with shearlets. Then we used a neural network just for what we cannot do otherwise, and then we combined both. So I don't have time to go into details in this, but I just want to show you and maybe convince you that it is very beneficial to actually combine both worlds on both methodologies. So this is original data. And we have a 60-degree missing angle. This is a crude reconstruction using what's called filtered back projection. This is the best model-based method. So there's nothing learned. We just use what's called Kutyniok regularization with a sparsity constraint, which maybe you also learn tomorrow a bit about. And you see this blurry part here and here. Then these are colleagues from South Korea who used just a neural network without any model-based component. And it's better than this, but not optimal. But I mean, if you combine both the model-based methods with deep neural networks, you see you get significantly better results. And this is another application. This is very classical edge detection and the detection which direction these edges have. And what you see here is from this image, this is what a human would recognize as an edge. This is what previous algorithms could do. And then with a neural network combined with model-based methods, you see you can, in a very detailed way, find all the edges and also color coding the direction of those. So this is the area of inverse problems imaging sciences. Now for PTEs, let me also show you one example there, and that's what's called the area of parametric PDEs. So these are partial differential equations where this is a differential operator, and you not only have, let's say, a right-hand side and want to compute a solution, but you have also a parameter involved, maybe a design parameter. So this parameter lives in RP, and so everything depends on the parameter. So the task is for a parameter, compute the solution. And typically this has to be done many times. The parameters are changed, maybe optimized, and each time the solution needs to be computed. And if P is large, this is a serious problem because there is a computational cost can be exponential in P. And what with a neural network, and there are also other methods which try to attack this. What we did now with a neural network was we showed that there exists a neural network which is actually able to compute this solution for all y, and we showed that the network does not scale exponentially in P, so we can keep the curse of dimensionality there under control. And this is in a way one advantage of these methods. And also numerically, one can see, and we drove extensive numerical experiments that in various different settings where we always chose a fixed neural network with 10 layers, which we then trained, that the neural network solutions are all very stable in some sense, and also very close to the true solution, and the performance also numerically doesn't suffer then from the cross of dimensionality. So this was just, let's say, 2 or 3 examples to show you how I came to that from the area of inverse problems imaging sciences and PDEs. And I think in this area, one main direction is how to combine actually this data-driven world, now this new brave world with neural networks, with what we did before with model-based approaches. So that's, I think, also one very exciting direction. But now let's come back to this list of topics which we already saw before, and I would like to now delve a bit deeper into the area of expressivity and then the area of interpretability. Okay, so expressivity, what is it about? Well, I mean, it asks questions like which architecture to choose for a particular application, what is the expressive power of a given architecture, maybe what effect has the depth of a neural network, if we approximate with a neural network, what is the complexity, does the complexity suffer from the curse of dimensionality? So it asks the basic question, which impact does the architecture we choose have? A bit more mathematical question is, we have a function class, we have an element of the function class and accuracy. We ask questions like, does there exist a neural network which approximates this function with that accuracy? And then which complexity does this approximating neural network have? And to delve a bit deeper there, what I would first like to do is I would like to give you one slide recall of what people are interested in function approximation anyhow. So in what people did before, in a sense. And so then we will come to neural networks. So in general, in this area of approximation, the key question is always the following. One key question. I have a class of functions. Let's live now in a Hilbert space L2RD. I have a representation system, maybe Fourier basis or wavelets or what you're familiar with. And then I want to ask, how good is this maybe also normal basis or representation system to approximate elements in C? And the way people went about that is as follows. So I take an F in my function class, and I have a budget capital N, and I'm allowed to choose capital N of these elements of my representation system, and I'm allowed to build a linear combination of those. And I want to do it in such a way to best approximate F with that budget. So that gives me then an n-term approximation, a best n-term approximation, and the error which I make is the error of best n-term approximation. So then I can let the budget go to infinity. I take more and more elements. That will, if this is a representation system, it will converge to 0. And the interesting part is at which rate does it converge? So at which rate n to the minus gamma. So the larger gamma, certainly the better, because then with very few terms, I can already represent F in a very good way. So this relates the approximation accuracy to the complexity of the approximating system in terms of sparsity, because I'm interested to take very few terms to approximate. And let me also show you one example of this. So a representation system and a function class where we actually know the optimal rate, and this representation system achieves that. So if you're familiar with wavelets, this is an extension of it. These are systems where the elements in the system look like this. So you have one function which you shift around in R2. You have another way, another matrix which zooms into the signal in an anisotropic way. So you see it zooms in anisotropically, so directional based. And I have a parameter which changes the orientation. So this creates functions which look like this, which you see here. The real definition is a bit more complicated than this, which you see here. Basically, what it aims to do is in Fourier or frequency domain, it aims to tile the frequency domain in a highly directional based way. And so here you see one of these shields again. And then, I mean, one can show that for a certain class of functions, which are called cartoon-like functions, I don't want to go too much into the details, but the way they look like is they are defined on a unit square, and they have a distinctive discontinuity curve. So these are functions which are governed by some discontinuities, and this is considered a good model, for instance, for images, and would be also for if you do classification. And for this class of functions, one can show that the error of best n-term approximation behaves in this way, and this -1, so this is the best possible rate. This one can show, and so up to a log factor, these systems give really the optimal approximation rate. So this gives one example of here. We now have this class of cartoon-like functions, so with this distinctive discontinuity curve, and if we take shearlets here, then we get up to this log factor the optimal rate n to the -1. Okay, so now we want to bring this to neural networks. So now the first question is, what is actually the complexity now of a neural network if we want to use that for approximation? And so this we already saw before, that's the same slide. And what we now choose as the complexity measure is we count the number of weights. So what we do is, so this L0, well, it's not a norm, but what it does, it counts the number of non-zero entries in the matrix and of non-zero entries in the vector. Yeah, so this is related to what I said before, sparse connectivity, that we have very few weights which are not equal to 0. And so then, I mean, we'll use, but I will say that each time, maybe this, sometimes this notation where we are interested in the number of layers, complexity, the input dimension, and the activation function. So why is sparse connectivity that interesting? Well, I mean, usually if you train neural networks, sometimes they are huge, they have hundreds of layers, and in particular also storage is a challenge. And this was also recognized, for instance, in this application of speech recognition, where before speech recognition could be only performed in the cloud because they are, the system could be stored, but now with new systems, we can do that also offline. And one main key aspect of what made this happen was the fact that we actually now have sparsely connected neural networks. So here, I mean, a key challenge is now we again want to approximate as accurately as possible, but then we want to compare this with the complexity of the approximating object, which is now a neural network, in terms of sparse connectivity, because that's our complexity measure. So we want to approximate with neural networks with very few edges. So that's the task. Okay, so certainly, I mean, we are not the first to do that. Actually, in fact, I mean, there were, let's say, 2 waves of research in neural networks. It's not something new. There was the first part where people usually considered what's called shallow networks, so with very few layers. But at that time, there was no possibility from the computational power to train deep neural networks, and also there was not so much training data. So because of these 2 facts at that point, things died out a bit. And then now we have the computational power and we have the amounts of training data. So now, I mean, they really took off. But I mean, at that point, people were also already interested in approximation properties. And so this universal approximation theorem is maybe the first big result in this area. So what it states is the following. So let's assume I have a continuous function on a compact domain. And let's assume my activation function is continuous, but not a polynomial. So then I can show the following, which I think is quite interesting. So for any accuracy, I can find such an object. So that's a neural network. We will go through that in a moment, which approximates this f with z accuracy. So how is this related to a neural network? Well, what you see here is, I mean, this is an affine linear function. Then you have an activation function, and then you just sum everything up. So this neural network looks like actually this. So you have here the input, you have the affine linear function, the activation function, and then you combine everything. So the AKs lie on these connections. Yeah, so this basically says, if I want to approximate continuous functions on a compact domain, I can do that with shallow neural networks. So there need to be a catch. I mean, otherwise things would be maybe too easy. And the catch is the complexity can be actually arbitrarily large because, I mean, this n, yeah, so this n could depend in a very bad way on epsilon. Yeah, so we cannot keep the complexity under control. Then there are many other results, and one other interesting result, I think, is from Jaworski, who looked at a bit different class of functions. So he now looked at S times continuously differentiable functions, again on a compact domain. He now chose rho to be a very specific activation function, and this activation function is actually the workhorse also for all applications now. It's called the ReLU, rectifiable linear unit, and it's the max of 0 and x. A very simple function, it is 0 and then x. Or maybe I should do it the other way around, 0 and then x. So what he showed basically was that there exist neural networks, so for each f, which depend, with the accuracy, depend on the complexity to the minus, and you see this s appearing in here and the dimension. Now, so the dimension actually appears in a bad way because it suffers from the curse of dimensionality, but still, I think one key and very interesting aspect is here, the accuracy is here directly related to the complexity. This is a very interesting result. Still, it's not optimal. And so what we want to do now is, from this sparse connectivity viewpoint, we want to understand how many connections do there need to be for a certain accuracy. So a lower bound, a benchmark result, and then we want to show that we can construct systems which actually meet that. And so for that, what we also need for the class of functions, we consider a complexity measure. So there are several ones. We chose something which is called the optimal exponent, but I mean, there are various other, I mean, for instance, also Kolmogorov entropy is the same. But so this is not, maybe let's not go too much into the details there. I would like to show you this lower bound result. So let's take an abstract learning procedure. So what does an abstract learning procedure do? Well, it takes an accuracy. It takes an element of my function class, and it outputs a neural network so that this neural network approximates that function with that accuracy. So that's in some sense what an abstract learning procedure would do. And now I'm interested in the complexity of these networks which I get here. And there one can show the following result. The product between epsilon to gamma, and so you see this is the supremum over all these complexities. This product goes to infinity as epsilon goes to 0. What does it mean? Well, I mean, it means that you see epsilon to gamma as epsilon goes to 0. This converges to 0. That means the complexity converges to infinity faster than epsilon to gamma converges to 0. So this, in a sense, gives you a lower bound on the complexity, which you definitely need, which you cannot go below. And so this holds for all gamma less than this gamma star of C. But that's a conceptual lower bound, which is independent of the learning procedure, which always these approximating neural networks need to obey. And then the question arises, if you're in the limit case, so gamma equal to gamma star of C, can we then construct neural networks which achieve this approximation so that this product does not converge anymore to infinity, but maybe to a constant? And so the way we go about this, and we could actually achieve that, is by building specific neural networks which mimic what we saw before. They mimic n-term approximations. So you have here, let's say, your representation system, and you build neural networks which represent or mimic each element of a representation system. And then to get a linear combination of those, you need to put them together and combine the outputs. So then if this would be, let's say, shearlets, I mean, each one would be one shearlet, then this would be a linear combination of shearlets. And with these, for these, in special cases, for instance, for shearlets, we could actually show that these neural networks, which we create that way, they meet the lower bound. So in that sense, they're actually memory optimal. So this is one of the results which we obtained there. So we showed that for these cartoon-like functions, which we discussed before, and for an n, I find a neural network where the complexity of this n, so that it approximates this function with that accuracy. And you see now this -1, this optimal rate also comes up again. So basically, I mean, one can show then that this is the optimal rate. So the first bound is sharp, and we can construct neural networks which actually meet this bound. And also along the way, it shows, since this you can do now for various systems, in particular what's called these affine systems like wavefits, shearlets, and so on. This shows that neural networks achieve optimal approximation properties of all affine systems combined. So therefore, this shows that neural networks are extremely good approximators, also due to the richness of their structure. And what we also saw, and I think what's also quite exciting, is now if you just take such an architecture and you train it on specific functions, then you can ask, what do these neural networks in these compartments actually do? What do they learn? So remember, before we put their, let's say, functions like shearlets in. And what they learn is quite interesting. So for instance, if you want to learn a function like this, just a function which is a classification function, then if I go back, in these compartments, the neural network learns functions which look like this. And if you're familiar with the theory, these are so-called richlets. And these are exactly, from a theoretical viewpoint, functions which you would take to actually approximate a function like this. And also this theoretical relation between the number of edges and the approximation error for this trained neural networks behaves approximately what we showed theoretically. And then if you make it a bit more complicated and you take a curvilinear singularity, again training your neural network, so taking points of this function and training your neural network to mimic this function, in these compartments you get functions which look like this. So these are like shearlets in some way, approximately. And again, this relation between the number of edges and the error behaves as we would expect theoretically. So this is, I think, one evidence which shows how powerful concerning approximation viewpoint neural networks actually are. So in here, I mean, we looked at the specific class of sparsely connected neural networks. So that maybe gave you a bit of insight in this area of expressivity, which is a very rich area. You can ask different questions, different function classes, different application areas, always wondering what is the best architecture? Can you get an optimal architecture from a certain viewpoint? So here we took the viewpoint of sparse connectivity and then got neural networks which are provably optimally memory efficient. So now I want to delve a bit for the last part of my talk a bit deeper into this area of interpretability, which is a very different area now. So this asks a very different question. So now we don't want to analyze the whole training procedure and so on. We have a trained neural network, which you can imagine in the future, you will actually have a lot of times, because there will be trained neural networks and algorithms, and you need to understand what they do. So we want to understand how it operates. You want to open the black box. So why is this important? Well, I mean, for instance, imagine you apply for a position, and at that point, we are already so far that job applications are maybe not only pre-screened by neural networks, but maybe even to some extent decided by neural network-based algorithms. And certainly, I mean, one would like to know why this decision was done, why this application was rejected. And so this is what this area aims for. And certainly one holy grail is, I mean, explaining a decision which is indistinguishable from a human being. I mean, we are far from that, but that's maybe one of the main goals. There are various different methods which you can pursue, and where people have made, I think, very interesting contributions. Gradient-based method, backpropagation, where people walk through the neural network, try to understand it. But most of those methods are not that theoretically based. And so what I would like to discuss with you now is one approach which we pursued, which also has a more theoretical foundation. So let's delve a bit deeper into the topic. And as usual in this area, we look at images. So let's assume, and this is also a classical example, we want to analyze handwritten digits, because some people have really terrible handwriting, and so it's good to have an algorithm for doing that. So let's assume here we have this 3, so you see the outline of the 3, and let's assume the neural network really decided this is a 3, and we want to know why. And such a, let's say, interpretability algorithm could then output something like this. So this color coding indicates which pixels are most important for the decision. And so if there's a gap here and here is actually really important, because of that, it's actually not an 8, but a 3. The blue parts here speak against it, because you see, I mean, this seems to almost close. On the other hand, if you want to wonder why this was decided to be an 8, I mean, then you see, I mean, this area actually speaks against it, and other areas speak in favor of it. So I mean, there we look now at what you could call it heat maps, or its relevance maps. So what relevance have the pixels? And what I would like to now show you is a rigorous definition of what relevance is by information theory. Via this, we can actually formulate this problem as an optimization problem, which makes it also accessible to, let's say, theory. And in this framework, we can also fairly compare different approaches. Okay, so let's look at the setting. We have a classification function. This can be a neural network, but can be also something else. And we have an input signal. And what we now want to do is we want to determine the most relevant components of X, so the components Xi, for this decision phi of X. And so let's assume X is an image. Then we would like to determine those pixels, this we call S, which are most relevant. The complement will be the non-relevant parts. And what we aim for is here to choose very few relevant parts. And we frame this in what's called rate distortion theory. So what is rate distortion theory in a nutshell? Well, I mean, you have 2 people, it's always Alice and Bob. Alice sends a message to Bob. She wants to send as few bits or as few information as possible, but so that Bob still recognizes the message. And so the rate is what Alice sends, and the distortion is the error which Bob, so the error in the receiver. So now, how do we phrase it here? So let's assume I have my neural network phi, Alice and Bob. They both have the same neural network. And let's assume I have my image, which is here recognized as a monkey. So now I would like to take a few pixels, the relevant pixels later on, and these Alice sends to Bob. Now, Bob has a problem because his neural network doesn't operate on just a few pixels. It operates only on an image. So we need to blow it up and obfuscate it. And so we complete it now with random pixels to not distort this meaning. And so then Bob can put this, what's now called Y, in his neural network and also gets the decision, and hopefully he gets the same decision, that it's also a monkey. And so this in some sense gives a meaning of relevance. So the relevant pixels will be those which, if you send them and then obfuscate them, put them in the network, give hopefully the same decision. So that's we will see that in formulas in a moment. Okay, so just to give it a bit more of notation, I have a random vector. This I need for this obfuscation, and so the Y, which you see here, is one part on S. It is XS, what I sent. On the complement, it is the noise. Okay. So now, so what is here the rate and what is here the distortion? Well, the rate is the number of pixels I sent. This I want to keep minimal. And the distortion is the error which I make. So phi of X minus phi of Y. Okay, so this is copied from the previous slide. This is, as I said, the distortion, the error, the difference. We take the square difference, and then here the expected value, because I have a random part in here in Y. And what I now aim for is I want to keep the error small, less than some epsilon. And I want to take the minimal possible number of pixels I can send to still have the distortion less or equal than epsilon. And so this I then call relevant pixels. So the distortion, the error is the smallest, is smaller than epsilon, and I take the smallest possible number of pixels. They don't need to be connected, and they can be just pixels. Okay, so that's nice. But I mean, if I just want to implement this, I actually have a problem, because this is NP hard. And let me just show you what one can show in this, how one can show this. So for showing that, we actually look at a very special case of neural networks which coincide with Boolean functions. So if you choose your network like this, I mean, you can encode a Boolean function, and then you can look everything in the binary setting. And so in this binary setting, one can then show rigorously that finding a minimizer is hard. So getting that this R of epsilon, so if I go back, so this R of epsilon was this minimal number of pixels I need to send. That this is less or equal than K is NP-PP complete, and approximating it is also still NP hard. This NP hard, I guess most of you are familiar with this. NP-PP is a complexity class coming from a complexity theory from artificial intelligence, which can be abbreviated by, I mean, planning under uncertainties. So you have one, let's say, non-random part and another random part, and you're wondering about success probability. Okay, so that's a bit a problem. What do you do when you have a problem? Well, you relax. So this is also what we do here. And so this is the problem which we saw before. You want to compute a relevant set, so a subset of the indices of the pixels. Obfuscate, this is the distortion, and this is the rate which we want to minimize. Now we make everything continuous. Instead of choosing and saying this pixel is relevant or not, we say this is maybe a bit relevant or maybe a bit less relevant. So every pixel gets now assigned a value between 0 and 1. And then we can also formulate an obfuscation by this dot product, which is the pointwise product with X and with the noise. That gives me now Y. The distortion I can compute in exactly the same way as phi of X minus phi of Y. And the rate, instead of counting the number of entries of S, I now take the little L1 norm. And if you're familiar with the theory of compressed sensing, you see this is something also what people did there. This would be the L0 norm, and then you relax to a convex norm to an L1 norm. And this you can actually compute. You can formulate it now as an optimization problem. You want your S to be box constraint 0, 1 to D. And you want to minimize the error, certainly the distortion, but at the same time also the little R1 norm. And so the lambda is this balancing factor between the distortion and S. And let me show you just some numerical results now to complete this part. So MNIST is always the workhorse in this whole area. It's always that example which people look at first. So now we have a fixed neural network with a test accuracy of 99.1%, which recognizes digits, and this we want to analyze. And so, for instance, for a 6, this is what different methods give us as an explanation, as a relevance map. So here are different methods, and this you see ours, the rate distortion explanation. And what you see here very nicely is that this open area is recognized to be important, which it also should be, because if it would be closed, for instance, it would be an 8. Other methods give other explanations, which might not be that well interpretable, and which are also not, let's say, that theoretically founded. But then you can say, okay, you have all these nice pictures, but I mean, it doesn't really tell me much. Can you actually compare also the results? And there, this framework also gives a means to compare, because now we can compare how many relevant pixels you choose versus the error in classification. Yeah, and if you look at the other papers, in some sense, they are also doing this, if they compare to other methods. Yeah, and so what you see here is that with a small rate, our approach has the least distortion. So you see the distortion goes down very quickly as you increase the number of pixels, of relevant pixels. Yeah, and so this is what we aim for. We wanted to have very few pixels which explain and which are those relevant for the decision. You can make things a bit more complicated. There's another, I mean, there are thousands of databases. So here STL10, this now contains images. Again, we take a fixed neural network. We get images like this. You see here, I mean, ours indicate that somehow the outline of the head is most relevant for the decision in the end. And then if you compare, you see also that our algorithm goes down the fastest. So with a small rate, you get already very small distortion. Okay, so I think my time is up, and let me conclude. I hope I convinced you that, I mean, deep learning is actually very effective for classical mathematical methods. I mean, that's how I came also to this area, basically, yeah, 5 years ago, in particular for inverse problems and partial differential equations. From the theoretical side, it's an exciting area because, I mean, right now there's a whole bunch of exciting theoretical questions. So the theoretical foundation is largely missing, and these are the areas which are indicated. So expressivity, learning, generalization, and interpretability. We then delved a bit deeper into these two areas. One, expressivity, where I showed you how to obtain optimally memory efficient neural networks, provably optimally memory efficient neural networks. And we also saw that neural networks are as powerful as basically everything which we did before. And for the interpretability, I showed you one approach which we pursued, where we have a precise mathematical, let's say, underlying mathematics, an optimization problem, and it also outperforms current methods. And with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much, Gitta, for your talk. That was really interesting. We have a couple of questions in the chat. So first one was Stephen Watson asked a question back when you were talking, you gave your PD example. Mm-hmm. So I might see if we can unmute Stephen actually, because so he can explain. Let me see if I can find him. Stephen, can you unmute yourself?
Yeah, I can. Thank you. Yeah, so
John.
wonderful talk. I asked a question back at the beginning. You put up a PDE example, and I just wondered what types of conditions you were assuming in the operator to arrive at that result.
Yeah, so there, I mean, so one has to say, I mean, these are linear PDEs. So you assume the canonical things like coercivity and so on. So what we do and what we aim for right now is to also go to the non-linear setting, but this is actually significantly more difficult. So here for the linear one, so basically also, I mean, how the proof goes is what you mimic in some sense. If you're familiar with a reduced basis method, so we in some sense mimic a bit of what reduced basis method does, showing that neural networks have at least that capacity.
I guess my question is partly my own training. I'm trying to link it to things I would learn as a grad student.
Okay.
So the solution operator for classes, say, of elliptic PDE, there's some beautiful, structural results and continuous dependence on, say, the coefficients, etc. So I'm sort of trying to work out in my mind the links between that type of classical analysis and these results. That's in some sense what I'm trying to do.
I mean, so you have this continuous dependency. We take elliptic operators, and the Y is, for instance, compact. So what's then underlying here is actually that if you look at just these solutions and you let Y vary, then the solutions move on a lower dimensional manifold. So that's the lower dimensional structure actually. And so this lower dimensional structure is what the neural network and also other methods then aim to detect.
Thank you.
Excellent. Thank you, Stephen. We also have a question from Milena. If I can also unmute her.
Yes. Hello. So thank you very much for your talk. It was really interesting. I was thinking when you talked about the imaging example, you mentioned Tikhonov regularization. And I think a lot of applications will need more and more advanced regularization techniques. I was thinking, for example, if you have a recommender system, you might want things like avoiding some violence or some inappropriate content in a way that it will not be black and white, like just don't show this image, but something like, if it has more violence or you have some measurement of violence, just try to keep that aside for a bit. So I was thinking if there's like any standard way of adding regularization when you choose the architecture of the neural network, or if you can maybe add it when you're learning.
Oh, I see. So you mean this slide here? This regularizer?
Yeah. For example, I was just thinking, is that the standard way of adding regularization, or is there any other way of adding of enforcing some properties in the output?
Yeah. So you could also enforce properties in this loss function, for instance. So for instance, for some PDE applications, you might not just take the square loss, but you might take some Sobolev norm or something like this. So there's basically a lot of flexibility, both in the loss function as well as in the regularizer. Then, I mean, there are also in this stochastic gradient descent, I mean, a lot of tricks to doing training, like drop out and so on. But for most of those, I mean, it's mostly heuristic. It's not clear which impact it actually has. But I mean, so I think the direction you spoke about, I mean, there's also a lot of, I think, exciting research to unbias already the test data sets, because that's usually the main problem, that test data sets are biased. And to recognize this already at that stage, because then it might be amplified actually during the neural network training.
Yeah, I was thinking sometimes maybe, even if it's not biased, like we might want to choose some things. So that's what I was wondering. Maybe there was something at this stage, in the learning stage, or in the.
Yeah, I mean, so that you, let's say, suppress maybe certain decisions.
Yeah, but rather than suppressing, I was thinking, well, I'm coming from like the linear algebra setting. So I was thinking, a lot of regularization techniques are just iterative methods that enforce some properties in the solution in a kind of more smooth way.
Yeah, I mean, if let's say you have a better understanding of let's say what you would like to maybe pursue concerning your bias, and you can phrase it in a here actually in a model-based way and can incorporate this in the loss into regularizer. I mean that's fine, but yeah. So if you have that at hand, I mean then it can be done this way. On the other hand, I mean also maybe these interpretability methods can also have an edge, because then I mean if you let's say see that you maybe get an outcome which you don't aim for, you can aim for understanding which features are most important and then maybe even retrain. So there are different possibilities to handle that.
Okay, thank you very much.
Excellent. I've got one final quick question before we move on. I was sort of, when you showed this rate distortion viewpoint, the first thing that sort of popped into my head was how it could be sort of linked to adversarial attacks and how to sort of train to make the network more robust. I don't know if you have any comments around that.
That's actually, that's also a very good question. We haven't tested that yet, but I think what would be there, as you say, I mean, exciting is to understand if you have, let's say, an adversarial decision, which features it actually highlights, because that will be quite erratic behavior in a sense, and maybe get something like an adversarial detector in some sense. But so I think that's an interesting direction, but so that's something for the future. Yeah.
Brilliant. Well, thanks again, Gitta, for a brilliant talk and an amazing start to the conference. So yes, thank you very much.
Thank you so much.
Okay.